Welcome. This week we're going to be talking about stoichiometry, which is using a balanced chemical equation and the mole ratios in a balanced chemical equation to predict how much product you can form in a reaction, or taking the amount of product that you want to form and predicting or figuring out how much of each reactant you're going to need to create that amount of chemical product. So this may seem, and for a lot of people this is a tough concept in chemistry, but I'm going to simplify it down and show you that you do calculations like this on a daily basis. We're going to use sandwich making turkey sandwiches over in the kitchen, to talk about these sorts of calculations and using the known ratios between ingredients that go into a sandwich to predict how many sandwiches you can make. So it's very similar to these stoichiometry calculations. So let's head on over to the kitchen. Okay, so here we are in the kitchen. I've gotten my sandwich making supplies. I have 21 slices of turkey. That's all I got. Unopened Tillamook cheese with 8 slices of cheese. And then don't have a whole loaf of bread, just have 10 pieces of bread in here. So my question to you is, how many total sandwiches can you make? So we're going to have a special recipe for our turkey sandwiches. We're assuming that one turkey sandwich has 1 slice of cheese, 3 slices of turkey, and like usual, you're going to have 2 pieces of bread. Okay, so pause the video with these ingredients, these numbers of things, and you can look up here. I have the recipe for a turkey sandwich. Pause the video, figure out how many total sandwiches you can make before you'll run out of one of your ingredients. Okay, so the big reveal. So 21 turkey slices. If we have 21 turkey slices, every sandwich is going to have 3 slices of turkey. So you probably can figure out that that would make 7 sandwiches. Okay, so you take your 21 turkeys. Per each one sandwich, you have 3 turkey slices, not 3 whole turkeys, 3 turkey slices. So if you take 21 divided by 3, you can make 7 sandwiches from those 21 turkey slices. Okay, so if the turkey is what was limiting, we can make 7 sandwiches, but we have a limited amount of the other ingredients. So let's take a look. With our 8 cheese slices, if there's 1 slice of cheese per sandwich, then we can make 8 sandwiches. Okay, and then the bread, if we have 10 pieces of bread and require 2 pieces of bread for each sandwich, I gotta go and bring this one over. We can make 5 sandwiches. Okay, so 5 is the least amount. We can only make 5 sandwiches because we will run out of bread after that. Okay, so we can test this, do some science, test this, make sure that that is correct. It's not really science, it's cooking. I have my apron on just for the occasion. Okay, so let's make some sandwiches, folks. Okay, so as you can see, I have run out of bread and I have made 1, 2, 3, 4, 5. Okay, I still have cheese slices left. I still have some meat slices left, so I could have made more sandwiches if I had more bread. But the bread ran out, and it was my limiting ingredient. Or in chemistry, when we're going to make an analogy to this, we have limiting reagents, or the reactant that goes in that limits the amount of product that you can form. So let's head back to the table now. Okay, so you may be thinking, why on earth did we do that? Well, I wanted to show you that you intuitively kind of knew how to make these calculations. So if you know that you have 21 turkey slices and you're going to need 3 on each sandwich, well, you know the ratio that there's 3 turkey slices per each one sandwich, so you take 21 and you divide by 3. Okay, if we were to write this out, like we do with our dimensional analysis, our unit conversions that we've done a lot in this class, you see that 21t, the t's cancel out. if you set up your ratio as 1 sandwich over 3 turkeys. And that gives you the math that you needed to do. 21 divided by 3 equals 7. Same thing with the cheese. In that case, you have 8 cheeses, 1 per sandwich. So you kind of automatically know that that will make you 8 sandwiches. And then the bread, which is what ended up limiting how many sandwiches you can make. We required 2 pieces of bread per every 1 sandwich. So we take 10b, and our ratio is 1 sandwich can be made from 2 pieces of bread. So we have our ratio of 1 over 2. When we multiply across the top, multiply on the bottom, we get 10 divided by 2, and that's 5 sandwiches. So the math is not going to always work out exactly like that. However, it's a very similar thing that we do with chemical reactions to make predictions about how much product you can form. In a balanced chemical equation, the ratios that you get from those coefficients are the mole ratios. It tells you how many moles will combine to and how many moles you will produce of each of your chemicals. So let's draw a parallel between this. Let's try to kind of turn this sandwich recipe into a chemical equation. So we can represent the turkey with a T. So the turkey with a T. Okay. We had in our sandwich, one of our ingredients or one of our reactants was cheese, C. Okay, our other reactant or ingredient, not really reactant, but we're drawing a parallel here. So our other ingredient that we needed was bread. Okay, and that's going to give us a sandwich, and we can write a sandwich down as like a chemical equation. Okay, we have 2 breads, B2, 1 cheese, and then we have our 3 turkeys. Okay, so, but this equation is not valid yet. It's not balanced. So what we're going to need to add are our coefficients. So in order to balance this, in the products we have 2 B's, and in the reactants right now, how it's written, there's just 1. So we need to add a 2 out front of the B. Okay, we have 1 C on both sides, so that's good. But our turkeys, we need to balance as well. So we have 3 T's in our product, only 1 T in our reactant, so we put a 3 in front of our T. Okay, recall that we can leave these blank, the coefficients for anything that you need 1 of, or we can go here. Okay, so this would be a balanced chemical equation for our sandwiches. The ratios that we used were these numbers. Okay, if we were going from figuring out how many sandwiches we can make from the turkey, our ratio was 1, which is our sandwich coefficient, because that's what we're trying to find, divided by the 3, which is our coefficient of the turkey, which was the amount that we knew, the amount that we were given and looking at. Okay, so this is very similar to what we're going to be doing with our stoichiometry calculations when we look at chemical reactions. We're going to use those coefficients of the balanced chemical equation for the reaction to make predictions about how much product we can form, how many moles of product, or we can then convert that into mass. Or we can go backwards and say, okay, I want to make this much product. How many moles of reactant do I need? And then I can convert that moles into mass. Okay, so if you haven't yet watched the mole conversions video, it would be a good idea to maybe pause the video and go back and watch that video so that you have a refresher. If you're feeling comfortable with converting between moles and mass, though, you're good to go and you can stay right here with me. I'm going to make my notes full screen again, and we are going to talk now about chemistry and how we can do stoichiometry, how we can relate the moles of reactants and products using our balanced chemical equation. So stoichiometry, the word is kind of long and cumbersome, but basically comes from the Greek stoichion, element, and metri or metron, measure. So we're kind of measuring elements, or it has to do with the amount of chemicals there are in the reaction, and we're measuring things. Okay, so from the word we kind of get some sort of meaning, but it's not a great explanation. So what stoichiometry is he's using a balanced equation to make predictions about amounts of reactants or products in a specific chemical reaction. So you know the amount of one or more of the substances in the reaction, and you're trying to make predictions or figure out how much you need of the other substances. And I can say this in words, but I've made a diagram that I hopefully will be a little bit better of an explanation. So the stoichiometry roadmap here kind of shows the mole ratio at this center. So the mole ratio is the ratio from the balanced chemical equation coefficients. Okay, so you'll need a balanced equation in order to figure out this mole ratio. Okay, so just like we did in the sandwiches, there's ratios of the different substances involved, and the coefficients of the balanced chemical equation are specifically in the units of mole. So in order to use this mole ratio, you have to be in moles of whatever substance you're given. So a lot of times in the lab, you're going to measure out the mass of the substance that you're putting into the reaction or the mass of the product that you get. But in order to figure out how much product you'll form from a given mass of reactants, or how much product you need, or how much reactant you need to put in to create a certain amount of product, you're going to have to first convert to moles and use the mole ratio in the balanced equation to go from moles of one substance to moles of another substance in the reaction, and then go on to figure out either the mass or the volume or the number of particles, whatever you care about. That mole ratio can get you there, but it's a number of different steps that need to take you there. You have to, the only way you can relate the amounts of substances in a chemical reaction is through the mole ratios from the balanced chemical equation. So in this video, we are just going to focus on mass to mass conversions in stoichiometry. Let me erase here. So actually, you probably want to keep that, but we are specifically going to just focus on this pathway here. Okay, so we're just going to go, given the mass of a substance that you're putting into a reaction, or given the moles of a substance that you're putting into a reaction, how much product are you going to form? And the units will be either moles that you're trying to find or mass in grams. So we're simplifying things down. But still, there's a number of steps that you need to do to solve stoichiometry problems. So I'm going to summarize the steps, and then we're going to do 2 practice problems that will hopefully kind of solidify your understanding of what this means and how you go about solving a stoichiometry problem. So the steps to solving a stoichiometry problem, the first thing you have to do is balance the chemical equation. So you have to figure out what your coefficients should be. Okay, and then you have to identify what is the problem giving you. And I have some tricks that I will show you when we do the practice problems. I like to identify and be very explicit. This is what I am given. This is the chemical that I know, and this is the chemical that I'm trying to find an amount of. So first thing you need to do, if it's not already in moles, you need to convert that given amount into moles. Then you're going to use your mole ratio from the balanced chemical equation, just like we used the ratio in our turkey example. Like if you have, in our turkey sandwich example, so if you had 21 slices of turkey, and for one sandwich required 3 slices of turkey, you need to use that ratio, that 1-to-3 ratio, in order to figure out how many sandwiches you can make. Same thing here, but you're using the mole ratio, and that comes from the balanced chemical equation. And then finally, you're going to, after you use the mole ratio, you know the amount in moles of the substance you're trying to find, but you then probably need to convert it to whatever desired unit. And for this video, we're just focusing specifically on if we are going to make a conversion at the end to a different unit from moles, then we're going to go into grams. Okay, so we're just going to specifically focus on that in this video. Okay, so let me scroll down here. And we are going to go over 2 different types, the 2 example problems. We will have one problem where you need to convert from moles of one substance in a chemical reaction to moles of a different substance using that balanced equation, and then we'll do a mass to mass question as well. From working through those 2, the mass to mass actually kind of has all the steps in it, so all the other 2 conversion, or the other two types of stoichiometry problems you could be asked to do on an assignment or on the quiz for this week would either be a mass to mole or mole to mass question. So I'll give you at the end a couple more example problems that you could try with in the description will be the solution and the answer to those final two questions. But we're going to work all the way through a mole to mole problem first, and then we'll work through a mass to moles problem second. Okay, and then you can do the other ones at your leisure. Okay, so the first question is a mole to mole example. So the question statement says, how many moles of KClO3 must be decomposed to yield 3.15 moles of oxygen gas? I have given you the equation, but you will notice that the chemical equation right here is not balanced. Okay, so first thing you need to balance the chemical equation. So you can reference past videos or past notes to figure out how to balance chemical equations. I'm going to just write in the coefficients here. So it'll be 2 KClO3 yields 2 KCl and 3 O2. So those are the coefficients there. So I've done balance the chemical equation. Okay. Before I move on to number 2, though, I personally do one more step. I identify what I'm given in the equation. Oh my goodness, I'm so sorry. Let me fix that. Make this bigger. Okay, so I like to identify that I am given an amount of oxygen gas. Okay, so this is what I'm given. That is what I know. Okay, that's kind of tricky right there. Given, and what I'm trying to find is this. I'm trying to find KClO3. Okay, so those are the two kind of important parts of my chemical reaction, and I need to be paying attention to those two compounds. Okay, so before I move on to step 2, also I like to kind of just set up the problem. Here's where, if you have those cards that we made, those will come in handy. So let me pull those over. So you're given moles in this problem, and then we had a card that says new moles over old moles. So I'll kind of explain. This is our problem setup right here. So we are given an amount in moles. Okay, we are given specifically 3.15 moles of the O2. Okay, so I know I'm going to need to take those given moles and I'm going to need to multiply by the mole ratio. So this is my mole ratio. Okay, and when I do my mole ratio, I always have the new moles, or the coefficient of what I'm trying to find. Okay, so in this case that would be the 2 in front of the KClO3 over what I was given, the old moles, or whatever I knew to begin with. So that would be 3. Okay, so I'm going to take this setup and I'm going to actually plug the numbers in and then get the answer. Okay, so my given moles, I know that I have 3.15 moles of oxygen gas that I want to create. O2. Okay, and then my mole ratio is going to be, I want what I was given on the bottom. Okay, the old moles. So that's what I started in here, moles of O2, what I know. So I get 3 moles O2. O is bad. O2, and on the top I have 2 moles KClO3. We need to decompose. KCl, that's a 3. Sorry, this does not write very well. Okay, and then I'm going to go ahead and I do the math with that. So I take 3.15, holy cow, times 2 in my numerator divided by 3 And when I do that, I think I get 2.1. Yep, 2.1 moles of KClO3. I gotta figure out. I might do this on my other. This is my personal computer. I think my work computer might write a little bit better on the touch screen. Okay, so that is our first example. Okay, and you will notice that I was given moles, so I actually didn't even have to do 2. 2 was done for me in the problem statement. I already knew the moles. Okay, the mole ratio I did in this step right here was my mole ratio. Okay, I was given moles of oxygen, so I put that in the denominator. My old moles go on the bottom, and I'm trying to figure out how many moles of the KClO3 needed to decompose. So I'm trying to find KClO3, so the coefficient in front of the KClO3 is a 2, so that goes on the top. Okay, I didn't need to do number 4, so number 4 I didn't need to do because moles were already my desired unit. That was what the question was asking, how many moles. Okay, so that is the first example. That's a mole-to-mole stoichiometry problem. Okay, the second example requires a couple more steps, but it's the same process that we're doing. You just have to do a step to go from grams to moles in order to use that mole ratio. And then at the end, you have to do an extra step to get to grams from the moles of what you're trying to find. Okay, so here is our second example, and let's read the problem. How many grams of oxygen are required to completely oxidize 162 grams of iron to iron 3 oxide? Okay, so this one, reading the problem, important like always. So how many grams of oxygen? So the oxygen, that's what I'm trying to find, are required to completely oxidize 162 grams of iron. So I know, or I'm given the iron, okay? And this kind of trips some people up. It doesn't matter if you're given a reactant, you're not always trying to find products. Sometimes you want to know how much of the other reactant you need to form a product, okay? Or you could have, you're dealing with a stoichiometry problem where you're looking at both products. A lot of times they are, one is in the reactant, one is in the product, but it very well can be that both are in the reactant or both are in the product. Okay, those mole ratios work regardless of whether you're looking at 2 reactants, a reactant and a product, or 2 products. So I've identified what I'm given and what I'm trying to find. I need to balance the equation. Okay, so again, if you need to review balancing equations, that's something that I'm assuming you do know how to do. So let's go ahead and add those coefficients in there. So when you balance this equation, you get a 4 in front of the Fe. You'll want a 3 in front of your O2, and you want a 2 in front of your iron 3 oxide. Okay, and then let's go ahead. Okay, so we're done with this. Okay, and we're going to set up our problem. So setting up the problem, again, I need to go into my typing mode so I can go get these guys over here. So let's drag these over. And I'll set this up. So in this problem, you are given mass in grams. Okay, the first thing you're going to do, according to this list over here, is convert the given amount to moles. So my given amount is in mass, so I'm going to need this card right here to get into moles of what I am given. Okay, and of course these conversion factors, they need a multiplication sign between them. Okay, and the next thing I'm going to be doing is use the mole ratio. Okay, so with my problem set up, use the mole ratio to determine the moles of the substance you're asked to find. Okay, so that's going to be this mole, old mole, new mole card, okay, that you made. That's red on the top, red on the bottom. So the old moles come from the coefficient. You're going to write there the coefficient of the given, so that would be a 4 in this problem, over the new moles. Okay, so in this specific problem, this is going to be 4 down here. That's our given moles. What we're trying to find is a 3, so that's going to be our ratio right there. And then, so we've completed step 3. Really struggling with switching between my mouse and my pen. Okay, so step 4, convert moles to desired unit. So that is going to be a mole to mass conversion card, because in the problem, I'm asking how many grams of oxygen. Okay, so how many grams, we can see that up here. So we're going to want to do one more step. And now we have our problem kind of set up for us. And then what you notice in this problem is that you actually have two things that you don't quite know yet. So you have these molar masses that you need. Okay, so you need the molar mass of what you're given. So our given, if we go back up to the equation, our given was the iron. Okay, so we're going to need the molar mass of iron. Okay, the molar mass of iron, that one's easy, straight off the periodic table, 55.85 grams per mole. It's not right very well. Okay, and then our O2 is what we're finding. And O2 is just going to be 2 times 16, or 32.00 grams per mole. Okay. So the last thing I have down there, it says plug and chug to get your answer. So now you're going to use your problem setup and your molar masses that you just wrote down to actually solve the problem. Okay. So this one gets a little long. Let me go ahead. I'll try to write a little smaller, but it gets pretty messy when I do that. So, so we're going to start with what we were given. So I was given in the problem way back up here 162 grams of iron. Okay, so let's go ahead and write down 162 grams of Fe. Okay, and I underline it. Okay, the first thing I need to use the molar mass to get to moles. So 1 mole of iron is going to be 55.85 grams. I get that from the molar mass. Okay, now I'm going to use my mole ratio. So I have 3 moles of O2 required for every 4 moles of iron. Okay, and then I need my last step to, because now if I stopped right here, I would be in moles of oxygen, but that's not what the problem asks. The problem asks for the mass of the oxygen. So I need one more step to convert from moles to grams. So my goodness, that is oxygen by itself. We want O2, 32. Okay, so there's 32 grams of O2 in every 1 mole. And finally, we now can write our equal sign. Okay, so if we go back and check our units, so we spent a while with dimensional analysis early on in the class, and then we kind of refreshed our understanding of dimensional analysis recently. But remember, when I set up these problems and I'm converting between one thing to another, I can always check that I've set it up correctly if my units cancel. Okay, so my grams of iron cancel with grams here. My moles cancel with moles of iron here. My moles O2, moles, and I'm left with grams of O2, which is what I want. Okay, so now I do the math. In order to do the math for this one, I multiply everything on the top. So I take my 162 times 3 times 32. When I do that, I get again, my goodness, get my pen. 15553, I think. Nope, 2. And then I divide by everything on the bottom, so I multiply 55.85 times 4 times 1. And I get, oh my goodness, I didn't actually write it down. I think it's still on my calculator. No, it's not. I'll do it. I want to show you guys the work. So 55.85 times 4, 223.4. Oh. Okay. And when I do the division, you should get 69.6 grams of O2. Okay, so those are two example stoichiometry problems worked through. I want you to check your understanding with these additional practice problems so you can do them on your own, and then you can check the description, the video description for the answers for these two practice problems. So I hope this gave you at least somewhat of an understanding of how we can use a balanced chemical equation to make predictions about the amounts of reactants or products that we need or will be formed in a chemical reaction.